Hello guys, welcome back to the channel. In this video, we are going to uncover one of the biggest invisible mysteries in electromagnetics, like what actually exists around every current carrying wire. Like we see wires every day in chargers, fans, motors and power lines. But did you know that every single one of them is surrounded by an invisible magnetic field that changed the history of physics forever? Also in this video, we understand the story behind Biot-Savart law and Ampere's circuital law and learn these important gate concepts without getting lost in lengthy derivations. So let's get into the video. Now imagine you are sitting in your room. There's a charging cable lying on your table. Generally, it is a simple copper wire. It's look completely ordinary. Nothing is glowing, nothing is spinning, nothing seems to be happening. But what if I tell you around that wire right now there is an invisible world? A world you cannot see, cannot touch, yet it is very powerful enough to move a compass, run electric motors, generate electricity, and even make MRI machines work. How actually this is happening? So, how can something invisible have so much power? This is a great question. Today, we are going to uncover one of the greatest discoveries in physics without memorizing difficult derivations. So, let's get into the chapter 1 before electricity. Okay, let's travel back more than 200 years. Scientists already know magnets. Everyone had seen a compass. Actually, a compass needle always points to north. People believed magnetic fields belonged only to magnets. If someone asks a question like, can electricity produces magnetism means, most of the scientists would probably say no. Because they looked completely different. Like electricity will flow only inside a wire, magnets will attract only to iron because they looked two unrelated worlds. But until one day, everything changed. A Danish scientist named Hans Christian Ørsted was performing an experiment on his table. That is, there was a battery, a wire, and a compass. The compass wasn't even the main experiment, it was simply lying nearby. Then he connected the battery. Now current started flowing. Suddenly, the compass needle moved, not slightly, but very clearly. The moment current flowed, the compass rotated. When current stopped, the compass returned. Now imagine his surprise, like nothing touched the compass. No magnet was nearby, yet something invisible pushed the needle, like something interesting is happened. That is, electricity creates magnetism. Now imagine a straight wire. Current flows upward. What happens around it? Can you see anything? No. Can you hear anything? No. But something extraordinary appears around the wire. That is, invisible magnetic field lines form perfect circles, not straight lines, not random shapes. Perfect concentric circles are appeared. Think of dropping a stone into a still pond. Water waves spread in circles. Similarly, current inside the wire creates magnetic influence spreading around it, except instead of water waves, they are magnetic field lines. This is why a nearby compass always aligns tangentially to those circles. The compass isn't pointing toward the wire, it is trying to align with the magnetic field. The magnetic field around a straight conductor is circular, not radial, not parallel, but circular. But wait, if the magnetic field forms circles, how do we know whether it goes clockwise or anti-clockwise? Here's the easiest trick you will remember forever. The right hand thumb rule. Fold your right hand. Point the thumb in the direction of current. Now curl your fingers. The curled fingers show the magnetic field direction. That is, thumb is equal to current, curved fingers is equal to magnetic field. So never ever memorize the directions, visualize your hand. In this concept, physics become much easier. Now scientists knew something amazing. Current creates magnetic fields. But another question appeared. That is, how strong is that field? If current doubles, does magnetic field double? What if I move farther away? Will the field become weaker? How exactly does magnetic field depend on distance? Scientists wanted a mathematical answer. So that's where our first important formula appears, that is Biot-Savart law. The Biot-Savart law tells us how much magnetic field is produced by a tiny current element. So here is the formula. Don't panic, don't memorize, instead understand what every part is trying to say. Current I, more current. More current means stronger magnetic field. Small wire element dl. Every tiny piece of wire contributes. Distance r. As you move away, magnetic field decreases rapidly. Notice the r square in the denominator. Farther distance means much weaker field. Sin theta. Maximum magnetic field occurs when the observation point is perpendicular to the current element. And when both lie in the same direction means it becomes zero. Think of Biot-Savart Law as adding contributions from millions of tiny wire pieces. Every small piece creates a tiny magnetic field. Add all of them together, you get the total magnetic field. This is why Biot-Savart Law is called the fundamental law for magnetic field due to current. So remember, Biot-Savart Law used for finite wires and arbitrary current shapes based on tiny current elements ideal gives magnetic field by summing contributions for each element. Here Biot-Savart law works beautifully, but imagine calculating magnetic field for a long straight wire or a circular loop or a solenoid. Adding millions of tiny current elements becomes very difficult. So they think, can we find magnetic field without calculating every tiny piece? Yes. When symmetry exists, there is a shortcut. That shortcut is Ampere's Circuital law. Now here is the formula for Ampere's circuital law. At first glance, it's look intimidating, but conceptually it's very simple. Imagine drawing an imaginary closed loop around a current carrying wire. Now walk along that loop. At every tiny step, measure the magnetic field. Add everything together. The total equals permeability into current enclosed. Notice something important. Only the current inside the loop matters. Current outside the loop doesn't contribute to the enclosed current. This is the concept which is very important for GATE exam. Always identify the enclosed current first. If symmetry exists like long straight wire, infinite sheet, solenoid, toroid, Ampere's law becomes incredibly very powerful. Now, what is the difference between these two, Biot-Savart and Ampere? Students often confuse these two formulas. Here's the easiest way to remember them. Imagine you are trying to calculate rainfall. One method is measuring every single raindrop. That is Biot-Savart, very detailed, very general. Another method is using the total rainfall recorded by a weather station. That's Ampere, much faster. Works only when conditions are suitable. So this comparison is very important for gate-like examination, so students don't confuse this Biot-Savart and Ampere's law. So the next time you see a simple wire, don't think of it just a metal. Imagine invisible magnetic circles surrounding it. Think about Hans Christian surprise. Think about millions of current elements creating magnetic fields. Think about Ampere discovering a beautiful shortcut hidden inside symmetry. That's the beauty of electromagnetics. You can't see the magnetic field, yet it's everywhere. Around every charging cable, every transmission line, every electric motor, every transformer. Invisible, but changing the modern world. So if you enjoying learning electromagnetics through stories instead of rote memorization, so stay tuned. We will uncover more invisible mysteries in the electronics. Share this video to your friends and do like and do subscribe to our channel. Let's meet in the another video.